So, let us start. So, we have introduced what is a Voronoi diagram in the last class. So, today we will see that how to construct a Voronoi diagram. So, what is a Voronoi diagram? A quick recap. You are given a set of site points and the objective is to divide the plane, the whole plane into set of cells, one corresponding to each site point, and that region corresponding to a site point contains a set of points which are closer to that site point than to any other site point. For example, for this site point, all the points in this region, the closest site point is this one. So, and we have given you few motivation to why to study this. This is a very early example of application of Voronoi diagram in 1854, where they have analyzed the cholera epidemic by using some Voronoi diagram, and the name of the person is interesting. Okay, so we have this. Okay, so so this is the formal definition of the Voronoi diagram, that S be a set of site points, and we would like to divide, we would like to create a set of cells among which contains the set of points Q such that distance from Q to Si is less than distance from Q to Sj for any other Sj. The formal definition of a Voronoi diagram. Okay. So, our objective is to create an algorithm which finds out Voronoi diagram. So, suppose again we do not want to solve initially the problem for where there are n site points. So, what we do is simplify the problem. Suppose we have only 2 points in the plane. So, this is my plane and there are 2 points, P1 and P2. Say these are the 2 hospitals and this is the outline of the city. And you want to find out from which set of patients the hospital at P1 is closer than to hospital P2. What will be the division? Very good. So, this is the perpendicular bisector of the line joining the points P1 and P2. If you see that all the points in this region, the hospital which is closest to them is P1 if compared with only P2. Okay, very nice. Again, one thing that we are assuming that no 3 points are collinear and no 4 points are co-circular, assuming a general position assumption. Okay? Now, the question is, if there are 3 points, then how the Voronoi diagram will look like. So, I have 3 hospitals, say H1, H2 and H3. How the Voronoi region of H2 will look like? So, forget that, for the time being forget about H1. I know that if I take this line, the perpendicular bisector of H1, H2 and H3, all the points in this side of the line are closer to H3. So, they cannot be closer to H2. So, these are out. Now, among the rest of the points, if I try to see that between H1 and H2, which points are closer to H2 than H1, what I will do? I will take a perpendicular bisector of the line joining H1 and H2. Clear? So, this is my Voronoi region corresponding to H2. Right. Now, the rest of the point, how to find what are the regions for H1 and H2? What I will do, I will join these two lines, take the perpendicular bisector, so all the points here are closer to H1 and all the points here closer to H3. Is it clear? So, some school level geometry. So, this is called a Voronoi vertex and these lines are called Voronoi edges. So, any other property of this Voronoi vertex? The circumcircle of the 3 points. Pardon my drawing. The center of the circumcircle passing through H1, H2 and H3. Clear? Okay, very nice. Okay, so and any other property? If I look at this circumcircle, why this is a circumcircle from any other point of view? This point, this Voronoi vertex belongs to the Voronoi region of H1, H2 and H3. What does it mean? That this is the closest facility from this point P to H1, H2 and H3. In other words, if I draw a circle centered at this point P and passing through H1, it should not contain any other side point. Can there be, suppose we are solving a case where there are 4 hospitals. So, there is a H4 here. Is it possible to have a H4 here? Yes, please raise your hand. If H4 is inside this circle, then what is the closest facility from P among H1, H2, H3, H4? H4. So, certainly H1, H2, H3 are not the closest facility. So, the property of the Voronoi vertex is, if you draw a circle centered at the vertex and passing through 3 of this closest point, that circle would be empty. Is it clear? Is it clear? Okay, very nice. There is no H4. Forget about the cycle, this line. Okay. So, if you understood this, say I take a point on the Voronoi edge, so the point is P, and I draw a circle passing through H1. I take a point P on the edge between H1 and H3 and take a point P on that and draw a circle passing through H1 and centered at P. Can we say some properties of this circle? It will pass through H3 as well, because this point belongs to the Voronoi region of H1 as well as H3. So, it has to pass through both the circles, and again the circle will be empty. The circle will not contain any other site points that is given to us. If we are given more than 3 site points, it cannot contain H2. If it contains H2, that means that H2 is closer to P than of that of H1 and H3. So, these are the two basic properties of a Voronoi diagram. So, let us move ahead. So, this is a typical Voronoi vertex, a cleaner drawing than what I have drawn. Okay. So, let us quickly jump to our design of algorithms. So, till now whatever I have told you, let us try to find algorithm by yourself. Can you give me algorithm to find the Voronoi diagram? Forget about Voronoi diagram. Can you give me an algorithm which finds only the Voronoi vertices? Rest I will take care of. Only Voronoi vertices. Just find out all the Voronoi vertices. The question clear to everyone? I want an algorithm which finds out all the Voronoi vertices, and I am given not 3 points or n points. Given n site points, and I would like to find out all the Voronoi vertices. How to do that?
Intersection of perpendicular bisectors will find the
Okay.
Choose 3 points, find the second vector and draw the circle and check if how many vertices.
Very nice. We have got two suggestions and both of them are right. I will come to them one by one. So, first is that what is the property of a Voronoi region? This is the intersection of n minus 1 many half planes. Can we say that? Can we say that? What we have? Suppose we have few points here. What is the Voronoi region corresponding to this? So, this is P1, this is P2, this is P3, P4 and P5. What is the set of points which creates a Voronoi region of P1? So, these are the set of points which are closer to P1 than to P5. These are the points, and these are the points which are closer to P1 than to P4. These are the set of points which are closer to P1 than to P3. These are the set of points which are closer to P1 than to P2, right. What are the set of points which are closer to P1 than P5? Lies in this side of the half plane. What are the set of points which are closer to P1 than to P4? P1 and P3? P1 and P2? So, how to find out the you see my point. So, this is the set of all points which are closer to P1 than any of the rest of the points. How to find this set of points? This is nothing but the intersection of n minus 1 half planes. Correct? And I can do it for all the side points, and I will be able to find the Voronoi region for all the side points, and eventually I will get the Voronoi diagram for all the side points. Still with me? There is another suggestion came that if we are interested in finding the Voronoi vertices, what is the property of a Voronoi vertex? If I draw a circle centered at that point and passing through 3 of the side points, this has to be empty. This is one direction. Is it a if and only if condition? Suppose I take a circle which is passing through 3 points and empty, does it create a Voronoi vertex? I take a circle. Suppose I find a circle which is passing through 3 points, say I found a circle passing through 3 points and which is empty. Empty means it do not contain any other side points inside. Can we say that this is a Voronoi vertex? Can we say that this is a Voronoi vertex? Does this point, say P, belongs to the Voronoi region of P3? Because what is the closest point from P? Closest side point from P? P3. Does it belongs to the Voronoi region of P4? Does it belongs to the Voronoi region of P5? So, this is a Voronoi vertex. So, it is a if and only if relation. So, another algorithm is take any 3 points, any 3 side points, find out the circle passing through these 3 side points, check whether they are empty or not. If they are empty, this is a vertex, otherwise it is not a vertex. Okay. These are the 2 algorithms that I have in mind. Yes, of course. So, he is suggesting that, I am repeating because of the camera, that he is suggesting that why can't we use a divide and conquer? Of course we can, but the question is then how to glue the two Voronoi diagrams together. Yeah, this is certainly one possibility, and there is algorithm that I will not cover. It is certainly possible to do that. Will not cover. Any standard textbooks on CG will have that algorithm. You can do that, a good idea. Certainly it is possible to find out a Voronoi diagram in using divide and conquer. But today we are going to use a different technique. So, how much time this will take? This will take order n to the power 4 time. N cube choices for the vertices, and how many vertices we have to find? N vertices. So altogether n to the power 4 time. Okay. So why it is n to the power 4? Yes.
We have to check if we have 3 vertex lies inside that.
So how many choices for 3 vertices are there? N cube, order n cube.
And then after finding the circumcenter, we have to check for every vertex if it lies
Inside or not?
that is n minus.
So you are with me, right? So what we have to do? We have to have n cube choices for the circle, and each circle you have to see that whether there exists another side point which is inside or not. How much time that will take? Order n time. So altogether this is order n to the power 4 time. But n to the power 4 time seems quite large, right? Is it possible to improve? Is it possible to improve this bound? Because we remember the last class what we have done, we have seen that you may have to end up reporting n to the n square points. So most likely there is no algorithm which is better than n square. Remember the line segment intersection example? If there are n square intersections, we need to take n square time because we need to report them. So it may so happen that the complexity of the Voronoi diagram is order n to the power 4. Number of vertices, number of edges, all together there may be n to the power 4. So there is no hope for doing better than that. So now we want to calculate that what is the complexity of the structure of a Voronoi diagram is. Is it clear? In other words, we are trying to count the number of Voronoi vertices, maximum number of Voronoi vertices that can be present in a Voronoi diagram, and maximum number of edges that can be present in a Voronoi diagram. Is it a pertinent question? Are you still with me? Are you confused? Please raise your hand, I will explain it once again. I am not in a hurry. Let us go slowly. Till now, is it okay? Please let me know if it is not okay. So, okay, so let us try to find out the complexity of the Voronoi diagram. So, let us go step by step. What is the complexity of a Voronoi cell? How many, what is a Voronoi cell, you understand? That is a set of points corresponding to a side point. So, this is a Voronoi cell. So, what is the complexity of a Voronoi cell? How many vertices there can be in a Voronoi vertex, in a Voronoi cell? for example, suppose I have so this is one cell. What is the complexity of this cell? 1 vertex, 2 vertex, 3 vertex. So, complexity of this cell is 3. What is the complexity of this cell? What is the complexity of this cell? 2. There are 2 vertices. I want to know what is the maximum number of vertices that can be present in a cell, in any Voronoi diagram. Two, 3, 4, 5. Correct. It's n minus 1. So there can be n vertex, there can be n vertex in a Voronoi cell. So, how many cells will be there? For each side point there will be a cell. So, there are n side points, total number of vertices can be n square. Total number of vertices can be n square. Is it clear to everyone? It is not clear. What is a Voronoi diagram? It is a collection of n cells, right? Do you understand what is a cell is? Cell is the region of each side point. How many vertices can be there in a cell? In this example, this vertex shares a cell with every other, that shares an edge with every other side point. This side point shares a edge with every other side point. So, how many vertices are there in each cell? N minus 1. So, each cell can contain n minus 1 vertices. How many cells are there? So, together they can have n square vertices in a Voronoi diagram. It is surely less than n square. It cannot be more than n square. Can it be more than n vertices in a cell? No. Can we improve this? Means, can we give a tighter calculation to bound the number of vertices? So, this is the theorem that we would like to prove. The maximum number of vertices is at most 2n minus 5 and the maximum number of edges can be 3n minus 6. This is what we will show. How to show this? What is the Voronoi diagram? Is it look similar to some structure that you know? This is a planar graph, right? And for planar graph, what we know? Where NV is the number of vertices, NE is the number of edges and NF is the number of faces. This we know, right? But there is a small glitch that Voronoi diagram is actually not a planar graph because there are half edges present in Voronoi diagram. What are the half edges? This is a half edge, right? This is a half edge. This goes to infinity. So, it is not a planar graph. Planar graph needs to be, the edges has to be between two vertices. This edge is between this vertex and to infinity. So, strictly speaking, it is not a planar graph, but we can make it planar by adding a new vertex here. We add a new vertex V infinity here and add all the half edges to this. So, I am just overcounting by 1 and constant I do not care. Okay? Are you still with me? What is the number of faces in this diagram? In any Voronoi diagram, what is the number of faces? N, right? The faces are the cells, Voronoi cells. How many cells are there? N. So, number of regions, number of faces is order n. Now, just do a simple combinatorics that what is the degree of each vertex in a Voronoi diagram? What is the degree of each vertex? What is the degree of this vertex? Okay. Okay. How many Voronoi region it can share? Can it share 4? Suppose I have a vertex like this. Possible? If I draw a circle passing centered at P and passing through S1, S2, S3, S4, there will be a cycle passing through centered at P, passing through all 4 of them. But what is our general position assumption? No 4 points are co-circular. We do not need this for this proof, but you keep that in mind that each Voronoi vertex has degree exactly 3. Does not matter for this proof, because we have a general position assumption that no 4 side points are co-circular and no 3 lines are collinear. From that we know that the degree of each Voronoi vertex is 3 and it is at least 3. That is the fact that we are going to use. Even this is a co-circular, that does not matter here, but keep that in mind. But we have added another vertex V infinity which has degree more than 3, right. So, I have given an example that, so you take, I am sure that this is very easy to follow for all of you, that how this is happening, but I want to give you a small example. Suppose we have 3, 4, 5, 0, 6, 2, 1, 1, 2. What is the sum of these numbers? The point I would like to make is, there are 3 ways to calculate the sum. One is I will sum all of them, or I can sum the rows. This is 9, this is 12, this is 8, this is 4, and sum all of them. Or I can do, this is 4, this is 11, this is 9, sum these 3 numbers. Both of them will give me same answer, right. Let us see why I have said this. Suppose I want to find out the sum of the degrees of this graph. Sum of the degrees, you know what is a vertex degree is. Everyone knows what is a vertex degree is. In a graph, degree of a, suppose this is your graph, degree of a vertex is the number of edges incident to that vertex. Suppose our objective is to find out the sum of the degrees. How to do that? First method, I can sum up all the degrees of each of the vertices. And if I do that, I will get a value. From that I get this, because each vertex contributes how much towards a degree? At least 3, right. Now if I count from the edge side, each edge contribute how much in the total degree? 2, because look at this edge, I am counting, this is contributing 1 to this degree and contributing 1 to this degree. See, each edge is contributing twice, exactly twice. Are you with me? Should I explain it once again? So, sum of the degrees is equals to twice the number of edges. This is a basic Lehmann graph theory. Do we have this? And we know the number of faces is everything, and if you take this too, we have this one and put it everything in the Euler's formula, what we will get is this, because I know the number of faces is exactly equals to n, is equals to number of side points. Basic counting, even not commutative, basic counting. Are you okay? And this is a very useful technique actually. You do it twice or thrice, then you do not even have to write this, you can directly write this. This appears in many places. And this is the way to think about the solution. Still with me? Doubts? Clear? Okay, let us move on. So, we have settled down the thing that the complexity of the Voronoi diagram is linear, that is order n, because what is the number of edges? Is the number of vertices is 2n minus 5 and number of edges is 3n minus 6, everything we just ignored the constants and it is order n. ठीक है? Okay. Now come to, we earlier had n to the power 4 algorithm. Now this algorithm actually is given by one of your friends. So let us come to this algorithm. So this is the intersection of n minus 1 half planes. How to compute this in n log n time? We can do this. You can't do this in n log n time. I have not taught you well. So together I need to find out the side points for n cells. So together it is n square log n. This is the complexity of the algorithm where we are taking the intersection of n half planes to find out the Voronoi cell corresponding to each side points. A great improvement over the previous one. We have n to the power 4, now we are in n square log n. Doubts? Okay. Another one we can do is also an incremental construction, that we will add the Voronoi, the side points one by one and keep changing the Voronoi diagram. If you go through it, I am keep all these things, because so that when you read about this you will get a clear idea. I will not cover this algorithm, but if you go through it, it will take order n square time. That what I will do, I will add side points one by one and maintain the Voronoi diagram. If I add a new side point, how many edges it can introduce? N many. So roughly in n time you can add a new vertex. So you have to add n many vertices. So the vague idea is that in n square time you can do that. One more improvement. There is one you can try from convex hull, and you will see that it will give you again n square time to compute the Voronoi diagram. Now, the question is, can we beat this n square bound? Is it possible to beat this n square time bound? Obviously yes, that is why I am here, and let us see how to do it. So, there are two methods, actually there are three methods. One is already suggested by him, that is divide and conquer, that we will not cover. You can find out a Voronoi diagram in n log n time using divide and conquer, that I will not cover. I will cover the fortune sweep line algorithm, a sweep line algorithm that we have seen till now, and I will give you some idea to how to connect a Voronoi diagram with a convex hull in 3D. I will give that idea, but for the time being let us directly go to the fortune sweep line method. Forget about the name fortune, what we are trying to do is a sweep line method. So, I have taken two classes on sweep line, so please let me know how to proceed. I have n side points, I will sweep a line, and I would like to find out, and I would like to create a Voronoi diagram for the side points. So, for this I will sweep a line from above to below, but same as left to right, you can do it using left to right as well. Just I am in a different state of mind, so that I have created the slides from above to below, but the same arguments holds when you sweep from left to right, you can argue exactly similarly. So, when we design a sweep line algorithm, what is the first point to concern is event points, right. You have to find out where to stop, what structure to maintain, that is the status. Where to stop while moving a line from top to bottom? Raise your hand. What? Where to stop? This is general hunch. There is no mathematics, there is no computer science, nothing. I am sweeping a line from top to below, where I should stop to change my data structure. Where the changes are happening? Side points, right? That makes sense. So, first guess is we have to stop at the side points. Good guess, but there is a problem with the guess. Can you tell me what is the problem? So, I am sweeping a line from top to bottom, and I am trying to find out the Voronoi diagram, and where I am stopping at the side points. What is the problem with this approach? The problem with this approach, if you think about this, is look at this point. Have we encountered this point yet? We do not know anything about what is below the sweep line. That is a basic assumption. I know everything about what is above, but I do not know anything which is below the sweep line. But this point has already contributed to the Voronoi diagram. This point, say call it Pi, has already contributed to the Voronoi diagram before we even encountered this point. Does not matter how you sweep, from left to right, top to bottom, right to left, whatever you do, this problem will arise. Do you understand there is a problem? There is inherent problem in the sweep line method. We have not encountered Pi, but Pi has already contributed. Hmm? How you will do that? I don't know, it's possible. I am not saying that it's not possible. It's not immediate to me how to do that. That's a good suggestion, angular sweeping or angular sweep line. That has been done in many problems. I don't know how to solve this problem using that. Okay. So this is a very basic example. I am sweeping a line. I have encountered just one point till now, sweeping a line from top to bottom, and I have only encountered one point P, one side point P, and this is my sweep line. Can you tell me which are the set of points which are above this sweep line which will be definitely be part of the cell of P? What does it mean? That there might be several points here, 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 but what are the set of points which will be, does not matter which points, how they come, can we say that this set of points will be always closer to P than any point below the sweep line? I am looking for a set of points, say Q, which are closer to Q, so closer to P than any point below the sweep line. Very good, one answer. So we are, in other words, we are looking for a locus of a point which is equidistant from P and the sweep line. I am looking for a locus of a point which is equidistant from P and the sweep line. What is a locus of a point equidistant from a point and a line? What is the locus of a point which is equidistant from a circle? Sorry, a point is a circle. What is the locus of a point which is equidistant from a line and a point? If it is not clear, go back home, just do some algebra, it will be clear. Right? So I know that this set of points which are lies here definitely going to belongs to the Voronoi cell of P. Is it clear till now? Okay. So if it is clear, let us try to extend this to 3 points. Now, instead of 1 point, I have 3 points. I want to find out the points above the sweep line which are closer to one of these points than to any other point below this sweep line. This will be union of these 3 parabolas. How they will distribute the points among themselves is a different question. Are you convinced that if I take any point here, that will be closer to, above this line, above this curve, that will be closer to the point, say P1, P2, P3 than any points below the sweep line? Right? So, how long you have been to Kozhikode? All of you? Just few days, right? 4 or 5 days. Have you been to the beach? Not yet? You should go. So, this line, this curve is called a beach line. Why? Have you seen the patterns the water makes in the beach? It looks like this. So, we have two curves. One is a sweep line, another one is a beach line. I cannot certainly say that a point here will not contribute anything here, but I can certainly say that a point here will never be able to contribute anything above the beach line. Clear till now? Questions? Questions? Okay. So, there are vertices, or there are points in the intersection of the beach lines, right? So, this is one such point, this is another such point. Let us see how much you have understood. So, suppose this is a point Q. What does this point Q signifies? So, these are parabolas, and now we have more than one parabola, they intersect at some points, and I am taking one of these intersection points and I am calling it Q. Question to you, what does this point Q signifies? Vertex, okay, one suggestion. Why? Think. So, I know that there are only two options, Voronoi vertex, Voronoi edge, side point, three options maybe. Side points is too much maybe to think of, but think logically. What is this point? This is the intersection of two parabolas, right? This distance, let us call it d. Is it same with any other distance? P1 to Q. Why? This is parabola, very good. And Q to P2. So, this point is equidistant from, right, and this is, if you see, this is circle is empty. This point lies in a Voronoi edge. This point Q lies actually in a Voronoi edge. So, this is how our beach line changes when the sweep line changes, and these red points are called break points. Okay? This is called break points. This is a reiteration of what I have told you just now. And when a parabola changes, when the sweep line changes, this parabola changes automatically. Then these break points also moves, and we know that the break points are on the Voronoi edges. So, when the line moves, these break points keep generating the Voronoi edges. I will show you actually how it actually happens. This is just a property analysis that I am doing. Think about, like, it is not super billions, but think about the first person who thought of that. okay, sweep line will not work, but why it will not work? This is the exact question he asked, where we can say that this is how he might have thought about it. And this is how you should also think when trying to solve a new problem. If a solution is not working, why it is not working? Can we exploit that fact somehow to design an algorithm which will work? So, this is how they will trace out. So, now come back to our favorite question, what are the event points? What are the event points? The first suggestion came is that when sweep line reaches a site point, definitely that has to, because something is changing. What is changing? What is new thing that is generated? A new parabola is introduced. If I move the sweep line epsilon amount of time, this will be the picture. This is my sweep line. When I reach a site point, it will introduce a new parabola to the beach line. So, I have to break the beach line and create 2 breakpoints and update the beach line. So, what I will do, I will insert this. I can keep beach line in a connected structure. I am not going into the details of the data structure because it is boring, but it can be done. I just insert, I will break this parabola into 2 parts and insert this new line into the parabola. And it will create a new edge at this point. It will introduce a new edge in the Voronoi diagram. So, when I show an animation, these things will be created. Actually, how this is happening? What are the other event point? Is there any other event point? So, one is site point, when the sweep line reaches a site point. Is there any other? So, once a parabola is introduced, does it going to stay in the beach line forever? At some point the parabolas will vanish, because the distance from that point will be too much, distance from the sweep line. That point we call a circle event. Circle event. That means before this parabola vanishes from the beach line, what will happen? 3 parabolas will meet at exactly same point. For example, here this parabola and this parabola meets exactly at one point. After this, this parabola will vanish from the beach line. What is the significance of this point? This is equidistant from 3 side points and to the sweep line. So, it will introduce a new vertex to the Voronoi diagram. And why it is called a circle event? Because there is a circle passing to 3 points which will be empty, and that is basically a definition of a Voronoi vertex. So, there are no other events to take care, and these events can be with, if you like, if you are a little bit careful, you can handle all these events very efficiently. Again, in log n time, each of these event can be handled, and all together we will have an algorithm with n log n time. So, because it is a beautiful algorithm, I can give you a detailed algorithm how to handle each of these event points and how to maintain a balanced binary search tree. I do not want to go into detail because it will ruin the fun of it. But take any standard textbook. If you do not have textbook, Google it. Voronoi diagram fortunes algorithm. They have plenty of algorithms which perfectly describes what we have to do in each event point. Okay. So, this is the example of what actually happens. So, this is how fortunes algorithm creates the Voronoi diagram. This is exactly what I have described to you just now. Circle event, site event, everything is taking place one by one. And this is not mine, this video is not mine. I have not created, I took it from web. This is a good exercise to create this video and forward it to me so that I can use it in my next presentations. So, this is how to find out a Voronoi diagram using sweep line. I will give you some idea about the other case as well. So, this is an algorithm which connects Voronoi diagram in 2D to a convex hull in 3D. It is not difficult. It is not difficult, right? So, you have to believe me that if you can find the vertices of a Voronoi diagram, that is enough. You can construct rest of the thing in order and time. What is a vertex in Voronoi diagram? Why a point is a vertex again in a Voronoi diagram? Why a point Q is a vertex in the Voronoi diagram? Because there exists a circle centered at Q which is passes through 3 of the side points, which is empty. In some sense, I will not go into the details, in some sense, while looking for the Voronoi vertices, we are looking for the maximal empty circles. Does everyone understand what is the difference between maximal and maximum? What is a, if you consider a Voronoi vertex and a circle passing to 3 of the points, if you increase it, it will contain some side points, right? You can show that this is the all possible, Voronoi vertices are all possible maximal empty circles possible. Like I am not talking about the infinite circles which are outside the convex hull. So, our objective is to find maximal empty circles. What is the equation of a circle? right? Right, this is the equation of a circle. Now suppose I am doing a transformation. So transformation is a function by which I am taking each point in R2 and projecting the points in somewhere in R3. How I am projecting? I have a point x and y in R2. I am creating a new point x, y, and the value of the z coordinate is x square plus y square. This is my new function. This is just a definition and I am defining. But now I will ask you, with this transformation, how a circle will change? What a circle? A set of points. What is a circle? Circle is a set of points, right? How this set of points will be mapped in a 3D? Don't use your intuition yet. Let's go by x square minus 2ax plus a square plus y square minus 2by plus b square equals to c square. So if I substitute here x square plus y square equals to z, what I will get? Z minus 2ax minus 2by equals to c dash, new constant. What is this equation of? Plane, right? So a circle becomes a plane with this transformation. What I am doing? I am taking each point in R2, projecting in some point in R3. How I am projecting? How I am finding? I am just changing the z coordinate. The z coordinate is exactly equals to x square plus y square. So for each point xy, I am getting a point in R2, in R3. Now I ask you a question that how a circle is changing. Circles becomes half planes. Each circle becomes a, each circle becomes a plane in R2, R3. So while finding the Voronoi vertices, what we are looking for? Empty, maximal empty circles. In R3, what we are looking for? In some sense, maximal empty half planes. And what is that? This is nothing but the lower hull of your convex hull. I am not going into details of the analysis. You think about a convex hull, if you have a set of points. What are the maximum empty half spaces in R2? Is these lines. If you move this little bit more, it will not remain empty. So another way to think about convex hull is this is a collection of maximal empty half spaces. This is empty half spaces which do not contain any of these points. So this whole R2 will be projected in a paraboloid. You will have set of side points in the paraboloid, and to find out the Voronoi vertices, what you need to find is a convex hull of these projected side points. So, this is, I think, is enough to make you curious. If you are curious, go through the calculations, even though you do not need a book, nothing, just do the calculations and you will have your answers. This is a simple idea of how a Voronoi diagram is related to a convex hull in 3D. Okay? So, that is all for today. Thank you.